Okay, that's fantastic. Yeah.
Okay, can we start? Can I start?
Yes, please, guys. It's such a great delight to see Sean. He's talking about the radioactive decay,
That's right.
and
You see from the
particularly,
you see from the left picture, it is a yellow point. It is such as animation about the alpha decay. Yeah.
uh-huh.
And the next slide I will talk about this. Yeah. Okay,
Okay,
let's
fantastic,
start.
Sean. Yeah. Yes, please.
Okay, good morning, everyone. I'm Sean. Today, I'm going to talk about the radioactive decay and the cancer therapy. Since last week, we finished the concept about Hodgkin-Huxley model, and we did so much researches and some kind of study to find some parts of the microscopic particles and the knowledge about the chemical elements. So in the fields of the radioactive decay, it is also relevant to some parts of the some knowledge about the Hodgkin-Huxley model, especially some microscopic particles. So my presentation is divided by 5 parts. The first, I want to depict and introduce some microscopic particles. Since in the Hodgkin-Huxley model, there has a circuit diagram. So there has so many electrons. So the electron is also belongs to the microscopic particles. It is too small that you cannot see from your eyes. And the second part is a great female called Marie Curie, and her whole life study of the radioactivity. And the third, what happened? And the third one is the radioactive decay in the mathematical modeling. And then I will give you some examples and some questions about this concept. You guys may try it and check it whether you can solve these questions or not. And the last one is the radioactive decay in the cancer therapy. So firstly, the microscopic particles. So we know that the matter or substance is composed of molecules. The molecule is the smallest particle that can be decomposed or break down to separate during the chemical change. It's a stable structure, and the atom this atom is a smallest particle in the chemical change. You see from the right picture, this is a model of the one atom. There has a nucleus in it and a proton and neutron. Outside of this atom, there are 3 electrons around it and rotate. So and the nuclear proton, electron, and the neutrons are the components of the atom. The electrons also known as the extranuclear electrons. As the name implies, they are particles that move around the nucleus at a very high speed. And the proton as an important part of the nucleus. So the most of the mass of the nucleus are composed by the proton. And the neutron the nucleus it consists of the protons and the neutrons.
Sean?
Yes?
Can you please go back to the previous slide? In this diagram of the atoms which you have, that's a beautiful picture that you just have there. But I come to one question. You have in your atom, the model of the atom which you have at the nucleus, 3 red dots.
3 red protons and 4 green neutrons.
That's right. You have 3 protons, 3 electrons, which it makes the atom neutral without having any charge. But
That's
you
right.
have 4 neutrons. What happened? Why do we not have 3 neutrons?
because the neutron, we have 4 neutrons. Because protons have the positive electric charge and the electron have the has the negative electric charge, the neutron does not have any charges, so the numbers is not necessarily.
But isn't like that the number of the protons should be equal to the number of the protons, neutron and protons?
The number of protons should be equal to the number of electrons.
And
so
how about the
they
neutrons?
have the balance. The neutron, I think, is not necessary to have the same numbers among these protons and electrons.
Okay, I'm just gonna ask my question. I'm okay so far, but I'm gonna go back to my question a little bit ahead when you have your speak about isotopes and the radioactive decay. We get back to the same thing because you may explain that on that stage there. Yeah, please go on. Thanks.
So secondly is a great physicist and chemist, Marie Curie. So Albert Einstein evaluated her as he said that Marie Curie is of all celebrated beings, the only one whom fame has not corrupted. That is a very high evaluation. It shows the great relationship between Einstein and Miss Curie. And it also shows her great achievement to the science and the radioactivity. So Marie Curie is Marie Curie is born in Poland in 19th century. She did great achievements and accomplishments for the isolating radioactive isotopes, and obviously she spent her whole life in the radioactivity, and she discovered the 2 elements, polonium and radium. These are the 2 chemical elements. She is the first woman to win the Nobel Prize. She is the first person to win the Nobel Prize twice. She is the only person to win the Nobel Prize in the 2 different scientific fields. So that is fabulous. And then is the radioactive decay. In the radioactivity, the nuclear reaction, and so all of the elements undergo the nuclear decay over time scales, so we can observe it. Some elements takes millions of years to decay, but most living things consist of isotopes. You know what is isotopes? Of carbon and nitrogen, which have such a long lifetimes that they never decay within the lifespan of the organism. And the radioactive decay is a process that unstable atomic nucleus, unstable element, it loses energy. It loses energy. The energy is reflected as a gamma ray, as a light of the gamma ray. You know what is gamma ray? By the radiation. So by using the gamma rays, energy releases. A material containing the unstable nuclei is considered radioactive.
And so sorry, one quick question I got here. So sorry about that. Very quick. Why some atomic nucleus, they become unstable and some of them are stable? I think that's how the distinctions between radioactivity happen.
Yeah, that's the point. So when the particles, the atomic nucleus becomes unstable, so they begins to radioactive. But if they are stable, they cannot do the radioactivity. Yeah, to change to another elements.
Okay. But is it the reason that maybe one of the reasons that the atomic nucleus, they become unstable, maybe one of the reasons is that, for example, the number of the neutrons are different from the number of the protons?
Probably. Because the neutrons, from the previous slide, the neutrons are four particles, but the electrons and protons are three. So
maybe one of the reasons is that.
maybe one of the reasons it becomes unstable.
That's right. Thanks.
And then there are two major points of the radioactive decay, which are the alpha decay and the beta decay. So it can separate from the particles that released, the different particles they released that separate to the between the alpha decay and the beta decay. So the alpha decay, mostly scientists use uranium 238 and by using the nuclear reaction to change it to the TH, which is the TH is one chemical element, 234, plus the hydrogen. The above from the left side, above the number is the 238 is the nucleus, and the below one is protons. So in the alpha decay, first U238 losses four masses and two electric charges, and change it to the TH, and plus is He. So four mass difference and two number of protons difference. So we can show this equation by using the general form, which is the left side is the M and the M and A, and the element is X. It changes to the X, changes to the M minus 4 and A minus 2 to the another element Y plus 4 and 4 highs. And so by remembering this, we can use the minus, because alpha decay is the minus point. It loses energy and loses mass. And but the beta decay, it plus the one electric charge from the TH, which is element, to the PA234. PA is the protactinium plus the one electric charge. The beta decay is from the TH234 to the PA234, but the mass difference is to plus. So alpha decay is the minus point, and the beta decay is the plus point. So these two decays always begins from the unstable chemical element, uranium and TH. But obviously, the two decays releases the energy, which is the gamma. So we can plus the gamma ray from the right side of the two equations. Okay, so what is the difference between the chemical reaction and the nuclear reaction? Some similarities about between chemical reaction and nuclear reaction is that the chemical reaction is conserve the charge and the masses. The nuclear reaction conserve the charge and mass numbers. And but the chemical reactions that we studied in the chemistry class, we all invariably we use the sign of the equal sign, but in the nuclear reaction we use the arrow to represent the progress about the reaction. This is a graph of the radioactive decay. You see the left picture. There are three functions. The blue one, the lambda is the largest one, and the green one, the lambda is the medium. And the right one, the rightmost one, the lambda is small. So it's like the slope of the functions. So it shows that the blue one, the radioactive decay, is the fastest one. It only takes about 6 seconds to decay from radioactive nuclei 1 to 0. But it takes over 10 seconds for the green one and the red one to decay to the 0. And the right side of the picture is the formula to calculate the radioactive decay, half-life radioactive decay. The A is the final amount, and the A naught is the initial amount. 1/2 is because of the half-life, so it divides 1/2. The time, it is the specific time of this nuclei. Which nuclei you calculate? Everyone has their own radioactive decay time divided by the half-life.
Sean, can you go back to previous slide, please? What is in your formula which you have, which shows that the final amount is that it's proportional to the initial amount, and you show that the half-life h, and on the picture you have gamma. What is gamma on the pictures, and what is the equation on the right side? How they are connected? What is gamma there? Gamma large, gamma small, gamma medium?
Where I have gamma?
Where is gamma on that equation?
This equation does not have the gamma. Where is the gamma?
What is a gamma then?
Gamma is the energy that is the light, that energy the nucleus, the atomic nuclei release.
But can we say also that it's going to be the half-life constant of a radioactive decay?
That's right.
Okay.
But there is also have the gamma decays, but it's hard to expand, so I just ignored it.
I think that gamma is different from that gamma radiation.
That's right. The gamma is different.
Or maybe we have to check that again. But I think that gamma is different from the gamma radiation. Maybe that's the half-life constants of the radioactive material.
Yeah, because the gamma radiation is hard to it's so confused to explain. So I just
that's right. But great job. Yes, please. Thank you. Thanks.
And the basic formula of the radioactive decay is that we have the first formula is to get the K. K is a constant number. As K is the number of the ln 2 divided by the time of the half-life, and the final amount of the mass or the numbers of the particles is equal to the initial amount times the natural number E to the power of negative K times T. T is the half-life time. And there's one example is that the half-life of oxygen 15 is 2 minutes. What fraction of the sample of oxygen 15 remains after 5 half-lives? So it is easy to solve that because because initially there has a 100% of the oxygen 15. It can be regarded as the number of 1. So 1 is as a nominator, and the denominator is 2 to the power of 5 is 32, because it decays 5 times, 5 of the half-life. So the fraction is 1/32. And the example 2 is that.
Can you please, Shasha, can you please go back to the previous slide, please, and also one before.
Huh?
Look at that. This gamma here. Look at that. When the gamma is large.
No, that is lambda, not gamma.
So what?
That is a gamma. That is lambda.
Oh, sorry. The concept which you have. This is the lambda which you have. Okay. Look at that.
Lambda is not gamma. Is the energy of the light, but lambda is like the slope of the function.
That's right. That's what I mean. The lambda which you have there. Look at that. When this is too large, the functions decay so fast. And if you go back to your next slide, please, to the example, and look at this, and minus K which you have there, K is K, and lambda, they are essentially the same thing. Your K here represents the lambda which you have on your plot.
Yeah.
Yeah, they are of the same nature, the radioactive constant, decay constant.
Yeah.
That's why you see that when lambda is too large, it decays so fast, because that's exponentially decay function that we covered. Essentially, that was a part of the lesson that we covered. When that
That's right.
constant becomes too large, the function exponentially decays so faster.
Yeah.
Yeah.
So,
Thank you. Thanks.
and the example 2 is that the sodium 24 has a half-life of 15 hours. If there are 800 kilograms grams of sodium 24 initially, how long the time it takes for this 750 grams to decay. So we know that we know that the time of the half-life is 15 hours, and the initial amount of the particle, the mass is 0.8 kilogram, and the time we want to know the time. So we just use the previous formula that the remain is the 800 minus 750 equals to 50 grams. So 50 grams equals to 800 times the natural number, which is 2.7 to the power of negative k. K is the log 2 divided by the time. Time is 15 hours, and then we can get the exact time to decay to the 50 grams. And the example 3 is that how many alpha and beta decay for the ray for RA and for RA to do the nuclear reaction to the PB. So by using the alpha decay reaction, that every time it will release four of the nucleus and two of the masses, and so 5 times 4 equals to 20, and so it will take 5 times of the alpha decay, but the remains of the particle X is there has 78 protons, but it will change it to the 82 protons. So it will goes 4 times, because every time it will release 1 electron to the reaction. So the answer is alpha decay is 5 times and the beta decay is 4 times. Yeah, and the radioactive decay in the cancer therapy. The therapy that uses a radioactive substance that gives off the type of high energy radiation called an alpha particle to kill the cancer cells. The radioactive substance is injected into the vein, travels through the blood, and collects in certain tissues in the body. Tissue means organs. No, tissue means organizations, such as areas of bone with cancer. You see from the right picture, there are some alpha particles and beta particles and gamma particle. Gamma to into the materials. That is the interaction of ionizing radiation with matter. And the next one.
Go back to previous slide. Let me see interactions of ionizing radiation with the matter. You have Bertrand log. This is a very advanced thing. Charged particles interact strongly and ionize directly. You have beta particles. It causes the, I should say, the ionizations, and the gamma. These are alpha, beta, and gamma. They are the radiation coming from the radioactive decay, and all of them, you mean that they ionize, I should say, the matter then. But okay, what is the importance? And also you have neutron bombardment, and the neutral particles interact less, ionize indirectly, and penetrate further. And what is the importance, I should say, of ionization, Sean? ionizing radiations, what is going to be ionized? And why is important?
Particle. Ion is one particle, but ionized radiation is I don't really know about the ionizing radiation. So
it means that, for example, there's a radiation, for example, like the gamma ray, and you have, for example, you have an atom, Sean. You have an atom which is neutral, which means that the number of the electrons and the number of the protons are equal. Then, for example, imagine that gamma radiation from the radioactive decay hits the atom, and it causes the electrons at the outer layer of the atoms just move away from the atom. Then the atoms becomes, I should say, ionized, means that it has more protons compared to the electrons.
Okay.
That becomes the ionizing radiation, and the matter becomes ionized. It means that there is an equilibrium between the positive and negative charges. But why is that going to be important in the cancer therapy?
Because it can kill the cancer cells or changes DNA, right?
Oh, interesting. Changes DNA what?
Damages the DNA of the cancer cells by the ionizing radiation.
Interesting, man. Interesting. Please move on. Oh, I love that.
And the radioactive decay therapy is the type of the cancer treatment that uses beams. Beam is light of intense energy to kill the cancer cells. Radiation therapy most often uses X-rays, but protons or other types of the energy also can be used. The term radiation therapy most often refers to external beam radiation therapy. So the right picture uses the protons to treat the cancer.
This is called the proton therapy, huh?
Yeah, proton therapy.
Oh my God.
Because 1/2 of the people with a cancer diagnosis receive the radiation therapy. So the radiation therapy play an important role to cure the cancers of humans and the development of the treatment of to beat the cancer, because the cancer is one of the most crucial illness for the for human beings. Yes, by using the radioactive therapy, some DNAs of the cancer cells may be damaged or may be changed, either slowing the progression or killing them. Okay, that's it. Thanks for listening.
Oh my God. Thanks, Sean. It was mind-blowing. Thank you, man. Thank you. I'm just clapping my hands. Oh, I'm so thrilled. It was a fascinating, truly fascinating, I should say, presentation. And honestly, I'm so pleased by the facts that you talked about the proton therapy, which I cannot have enough of it. Fantastic, fantastic. You open more research opportunities before we finish the classes this term, and it's going to be the proton therapy, which is a very fascinating field of the research.
But I really do not know what is ionizing radiation.
Oh, okay. I have an assignment for you then, Sean. Then. No worries.
Oh my God.
I'm gonna talk about that. We have a good assignment for you. Then thank you very much, Sean. I really love that. Please do one thing. Please send it to me, the PDF file which you have, because I have to just put that on the Schoology website because I have to mark you based on it then.
Oh, okay.
Awesome.